document I sent with the lesson from yesterday got to you, but nonetheless, today we will try to focus more on practical applications for in combinatorics. Okay, thank God this doesn't work again. Specifically, operations that we can perform and related problems that could appear. One of which I think was given to you today as K and N. Second task from today's contest. Okay, so okay, this won't ever work. Thank God. So yesterday we've spoken about groups and related operations that would happen on them and what they could entail. All of this to normally finally get to the following two notions that I will introduce right now separately. So while working in combinatorics or trying to solve counting problems, more recently, the approach that has covered problem setting from what I think used to be huge numbers in the very earlier years of competitive programming is to work under the group modulo P, that is performing all operations modulo P, addition, and multiplication, most notably. And trying to perform such operations such that we would get the answer that could otherwise be a very large number to get its equivalent residue modulo P. Oh, okay. No, okay, sorry. So, what is of greater importance is to try to be able to calculate operations that would normally stem out of this. Because maybe in combinatorics you've seen that we might encounter things such as binomial coefficients, most importantly, and powers of elements, a to the k, which normally, obviously, these would have a lot of digits. So obviously, while working under modulo, we'd have to figure out how to manipulate them. Yesterday, what I tried to cover was to finally get to the following point, that the group under addition clearly has dimension of P, but most importantly, under multiplication, it has size P minus 1. I can't figure out for the life of me why this works so poorly. So, because we would have only P minus 1 numbers that we could reasonably multiply and function together as a coherent operation. That is, we can't really multiply by 0, because upon multiplying by 0, we can't really go back to where we started. Obviously, because 0 would cancel out. But with the multiplication operation being a coherent one and being able to form a group thereof, we can state the following fact, that any element or any residue modulo p, where p is a prime, respects the following identity: a to the power of e minus 1 is equal to 1. Right now, if it isn't clear, we will unfortunately black box this, and I hope for further clarifications, would consult what I would not really, yeah, so I should maybe cover that. We won't go any further into group theory and the inner words that could help us. We will just keep basically today to, okay, my graphics tab, I really should change my graphics tablet because it's bad. But today I'll try to focus on, oh my god, it's really bad, I think. Today I'll try to focus on counting problems and notions that could reasonably appear within those. Let me try to change the tip of my pen because maybe that's the issue. Okay, now it might work a little better, I hope. Okay, it doesn't. Too bad. So today we will cover combinatorical identities, or combinatoric, I'm not sure what the adjective in English is supposed to be. Combinatoric identities and manipulation of operations modulo p, where p is a prime number, and related problems that would come out of this. So from yesterday, what I tried to explain is that ultimately, with multiplication being a coherent group, a to the power of e minus 1 equals 1. This is important for the following reason, that when, if, and when we would work with probabilities, and we will get into more details in another lesson, for instance, we would maybe have to divide by numbers. For example, if you'd ultimately want to excuse me for one moment, I'll just use my mouse and be done with it. Okay. When if and when we would work with probabilities, we might encounter the notion of having to divide by numbers or to provide a probability modulo some prime number, which normally is a bit stupid because in most correct mathematical terms, a number modulo p would be basically an operation that uh, we would perform upon the set of natural numbers. Okay, won't work really. So we'd expect to have a number n, and if given a number p, n would have to belong to the set of integers. And that would be more coherent to consider as the modulo operation. But probabilities aren't really coherent because how can we take the modulo, let's say mod 3 of 3.2? Then obviously maybe we can try to cancel out the 3 as we would normally do. Let's say if we would take 5 mod 3, we can subtract 3 until it gets to the range of 0 to 3 exclusively. But now we are left with 0.2, which doesn't really make sense. However, the reason fractions have been introduced into mathematics by means of rational numbers is because they are allowed to represent a number such that when multiplied, for example, a over b, when multiplied by b, would yield back a. And this is essentially what every problem actually has in its caveats whenever they would ask for a probability of p, that they aren't really asking for like a fraction or whatever. They are asking for a number such that it can be described by the such that if we were to take the real fraction of c over d that would accurately describe the result, we would have to print a number modulo p such that c times that number, d times that number would equal c. And as mentioned before, and this was basically an useless caveat for all of that, groups have the invertibility property. That is, any number should have a number that who would cancel it under the operation. So if we are to find the number x such that d times x equals c, it would be equivalent to find a number such that x equals d to the minus 1 times c. And because we ZP is a commutative group, it's equivalent with c times d minus 1. Normally order would matter in groups, but we can go beyond that. So since a to the p minus 1 equals 1, clearly what follows is that a to the p minus 2 times a equals 1. So a to the p minus 2 equals the much desired inverse of a. It will never really be the case, but for you or in any problems generally, hopefully. But we can also talk about such inverses modulo n, where n isn't really a prime number. But in such a case, obviously, there are elements that are not invertible. For example, modulo 6, then 2 does not have an inverse. We cannot multiply 2 by anything to get back to 1. Because anything we would multiply that element by, especially when taking modulo 6, would still be a multiple of 2. And 1 is not a multiple of 2. So whenever we are working modulo n, we would have to work with all the numbers a such that GCD of a and n equals 1. This is a special value that is called the, I'll make a new drawing. So to work with a such that a and equals 1. Then this operation under this set, which I will label as Tn, the number of the set of all numbers a less than n such that GCD of a and n equals 1. Under multiplication still forms a coherent group. So then obviously a to the size of this set will still be 1. That is a to Euler's totient function will be equal to 1. Again, if they are coprime. Okay, but we can disregard that. Normally, some other problems might. There's also Bezout's theorem. I will mention it just very briefly, but I won't get into details. That mentions that for any elements a and n, no matter their GCD, there exists a pair of numbers, well, multiple pairs at that, such that ax plus ny. I think there are multiple. I hope there exists at least a pair in any case. Yeah, at least a pair, such that ax plus ny equals their greatest common divisor. Some problems might this operation would then be, if we are to take all of these this expression modulo n, we'll have ax equals d mod n, where d is the GCD of a and n, which could be described as the soft inverse of a under multiplication with n. But this can be disregarded. It's called the extended Euclidean algorithm, the computation of the coefficients of x respectively y, and I won't get into it. It will be covered in the document that I hope to share with you. Okay, so as previously said, today's lesson will really try to be able to calculate, among other things, technically speaking, both powers of numbers modulo n and binomial coefficients. We are almost basically done with binomial coefficients for the following reason, that we now know that, well, in general, we know that binomial coefficients are the division of a factorial by two other factorials. So clearly, now we know how to divide by these two. Given that we could solve the problem of exponentiating a number to any power. We will now get into that. Tm. Oh, I missed that. Tn. Well, it's Tn, but my handwriting is horrible. Tn. Earlier, I've mentioned, sorry for not getting your message. I hope to get a ping, but I didn't. Tn will be the set of all numbers a, such that a is less than n, and GCD of a and n equals 1. And obviously, multiplying any two elements from this same set, and then taking the residual modulo n, will still yield back an element from this set, because we will not generate any new divisors because we never had any of them to work with in the beginning. So Tn under multiplication modulo is, I think stable group is oxymoron. No, not oxymoron, but repetitive. Okay. Normally speaking, the issue with raising any element to any power would be the fact that trivial approaches to the problem would yield back a result in O of x. The time we have to iterate from 1 to every exponent. That is, the trivial algorithm would clearly be for 1 to x, we have the result, and we multiply it back by a. What the issue with the algorithm, with this algorithm is that obviously there's a lot of redundancy. More specifically, for example, we only multiply by a right now. Not necessarily a natural thing, but a thing that we could think about is, given the fact that we only have 3 variables to care about in an algorithm, well, 4, because there's also the prime modulo, but no one cares about that. Given that any algorithm that would have to exponentiate, that would have to raise any element to any power would only have to work with a total of 4 variables, that is the exponent, the initial base, the result in which the result where the sought number will be accumulated in, and the prime modulo. We might find other combinations that would help us achieve the goal in something less. Many of you might know already, and I might bore you, that there is an algorithm in logarithmic of x. X clearly is not related to the calculation of R. P is not really related to the calculation of R because it will only, the only purpose of P would be to keep all of these numbers into int so we can calculate them. So the O of x algorithm only multiplies by A. But what if we would multiply by R? Well, trying to look at the logarithm of both R and A, we will notice that basically what we are doing is for 1 to x log of R plus equals 1, which is logarithm of A. Logarithm of A mod, logarithm of A in base A is clearly 1. So x times, we just increment by 1. Well, this number itself, for many times at least, for more than half times, half the loops. So for more than half the loops, log A of R is less than half, which is trivial because obviously for the duration of the first half, it's less than half. And so, yeah. So instead of only adding 1, we can try to consider adding it back to itself. That is multiplying R by itself. This would only help if x is an even number. So if x would be equal to 2k, for example, we can just calculate a to the k, and we can raise that to the second power, which really just means multiplying it back to itself. This idea would later lead us to try to consider what would happen if x would be odd. then if x were odd, then we would have to split it one time into a multiplication of a times something, and then the same multiplication that might occur under 2k. So a to the 2k, which we've earlier established that would look like this. So a times a to 2k, because a times a to the k times 2. This is now a new subproblem of its own. Let's say k equals 4t plus 2. A times a to 2t plus 1 to the power of 2, again, because we can divide k by 2, new subproblem, all raised to the power of 2, a times a to 2t times a to the power of 2 to the power of 2, and so on. This will obviously lead us, by the end, with a lot of residues like this one, that ultimately, upon breaking out the parentheses that we'd have here, for example, and distributing the exponents both to the left and the right, would yield back some values of a that we would multiply, some powers of a that we will multiply, all of which are powers of 2. And now finally that we see what shape the algorithm can take, we can later formulate it as follows. We can initialize an array, but not necessarily an array, p to k of k, such that p to k equals a to the 2k. So, for example, for k, this is 16. It's not 8, 2 times k. It's 2 to the power of k. A to the power of 2 to the power of k. Wait, I should look more often. Yes, I'm trying to explain binary exponentiation. Yeah, I'll work on the samples. It's a bit irritating because I don't know how to get paint for the messages. Normally I get. Okay. As previously mentioned, if we are to calculate a to the power of 2t, we can just calculate a to the power of t and then raising this to the power of 2, which just means a to the power of t times a to the power of t. Meaning, when we would want to calculate to p to k of k plus 1, which would be a to the power of 2k plus 1, this really is just a to the power of 2k times 2, which can be reformatted as a to the power of 2k, all of this to the power of 2, which just means multiplying it by itself again. So naturally, what follows is p to k of k plus 1 is p to k of k times p to k of k. To work more concretely, what is p here? Okay. P to k is an array that we've noticed is useful for our calculations. More specifically, when we tried to see the redundancies that we had previously, that is, the result we had was always multiplied just by a, and we had to do this x times. We didn't like it. we try to consider what would happen if at any stage we multiply r by itself. R normally at that point in time in the for loop that we have would be equal to some a to the power of I, let's say. If then at step I, then we would multiply r by itself, we would get a to the power of I squared, that is a to the power of 2I. And we think that basically what happened was that we multiplied the exponent by 2, clearly. If x were an even number, then we could do this step at when I is equal to k. Then that is at a k iteration of the original algorithm, where we just multiply by a over and over and over. Again, I remind we want to calculate a to the power of x mod p. In that case, when getting to the kth iteration of the algorithm, we would obviously get the sought result. So then we think, okay, if x would be an even number, we can halve on the operations that we did, that we would have done normally, which at the time doesn't really seem that impressive because we would go from O of x to O of x over 2, which is O of x again. But maybe this will lead us somewhere. We can have on the number of operations where we just multiply by a over and over and over. Two, that we can just halve on it. The other case that might concern us is when x is equal to 2k plus 1, because there will be no index when it would make sense to raise to the power of 2, to multiply r by itself. Because if we were to multiply r by itself, we'd get an even exponent. But that is not really a great issue, an issue of great concern. Why? Because we can say that the result that we want to have, a to the power of 2k plus 1, is equal to a to the power of 2k times a single a. And now that we have this a to the power of 2k, we can apply the algorithm that we've described earlier to obtain this value. But this value, upon breaking it down to the simple problem of calculating a to the power of k and then raising that to the power of 2, can then later be broken down by the same criteria, whether k is an odd number by itself or an even number. And what would happen is that every time there is a bit turned on in k, we will divide by 2 under this algorithm, which takes the problem of a to the x and reduces it to the power of calculating a to the power of x over 2, which is basically the square root, so to say. We would find that at any point there will be a need to add one such number, one such multiplication of a for every turned on bit. But when we would reverse the operations that we see, we will find that the final result, a to the power of x, is equal to whatever this breaks down also, so something, times a to the power of 4, which is really a power of 2, because upon multiplying this value upon multiplying this value, okay, the color, Okay, now I'm back. Upon multiplying this value by itself, we'd get a to the power of x over 4 times a to the power of 2 equals a to the power of x over 2 times a to the power of 2. Raising this again would get us, well, I've done some floors that might have not been visible, a to the power of 4. So we now have the intuition and we see that all that we really want to calculate and that could help us solve the problem much faster is all the values of a to the power of 2 or to the power of I. That is exponent a to the power of 2. This is ultimately what we want to calculate with P2K. P2K is an array, a collection of all such values. All the powers of A to a power of 2. As I've said, the recurrence for this is trivial because it requires that for a to the power of 2k plus 1, we just multiply a to the power of k, a to the power of 2 to the power of k with itself again. And so we can break down the calculation of a to the power of x as reading x in binary. That is, maybe x is 1 0 0 1 1 0 1 0 in binary, which is equal to I'll read okay, left to right. So this would be the most significant digit. I think that's wrong, but I don't know. With 2 to the power of 1 plus 2 to the power of 3 plus 2 to the power of 4 plus 2 to the power of 4. So this is 4, 5, 6, 7. 2 to the power of 7. Now, we know that a to the power of x is equal to a to the power of 2 to the power of 1 times a to the power of 2 to the power of 3 times a to the power of 2 to the power of 4 times a to the power of 2 to the power of 7. Which really is just a multiplication of some entries that we would have here. Some of these P2Ks. Mod P. Okay, I hope now this algorithm is clear. Normally, the way I entail the following algorithm structure. So, given a and x, construct the P2K array of all the powers of a to the power of 2 to the power of k. Then for bit from 2 to the power of 0 to whatever 2 to the power of 30, if x contains this bit, then the result is multiplied by the correspondent entry in the P2K array. This is a bit wrong. There are very few cases when this structure where we have to construct the P array is useful, and we'll cover those in other lessons. But right now it's a bit redundant, and it can be done much more simply because we can calculate this P2K on the go. That is, we do not initialize it in the beginning for brevity, and instead we write it as follows. So we initialize a value q to k equals just a. Then for a bit from to the power of 0 to the power of 30, if x contains this bit, then our result is multiplied by q to k. And then to make q to k relevant for the next bit, we multiply it by itself. So in this algorithm, what will happen is that initially q to k is equal to a. Then after one iteration, it is equal to a squared. After another iteration, it is equal to a to the power of 4. Another iteration is a to the power of 8, which really corresponds to the bits that we iterate upon and that we check whether they are contained in X. Normally here I'd ask if that is clear, and if someone wants to share any other concerns, they are free to do so now. Otherwise, I'll move on to factorials. Okay, I'll move on to factorials now. So the two fundamental operations, well, complicated operations, modulo k have, we are, okay, out of the two fundamental operations that we sought to calculate, we have taken down one of them. Now okay, it's funny. Now I want the colorway, and I just close it. So a to the power of x is done. Now remains to calculate and choose k. I'll mention a factoid that I think p minus 1 factorial equals, it might be equal to, let me check, is equal to minus 1 modulo p. Unfortunately, we will never get to use this because p will generally be large enough to not warrant a factorial up to it. Otherwise, this will later get, if you, actually, I'll just mention it very briefly. If you want to calculate some value like 10 to the power of, no, sorry, 5 times 10 to the power of 8 plus 6, 3, 5, 4, I don't know. If you want to calculate the factorial of a really large number modulo an even larger prime number, no, okay, not a factorial of a prime number, but just of any number, this can be solved with SQRT decomposition. And FFT, but most notably FFT as a multi-point evaluation. And I think the final complexity would look something like square root of mod times log times log. But this is a factoid that I leave up to you to dwell upon and to think about, but you'll never get to use this ever. Even if I were to explain it, it's useless. But I think it's fun. Okay. So factorials are very easily calculated normally. Because factorial of n is defined as n times, can be defined as n times n minus 1 factorial, which is then n times factorial of n minus 1. So basically what we can do to calculate all the factorials and then later the binomial coefficients is to initialize an array with fact 0 equals 1, and then for I to 1 to whatever value we want, we just take the earlier value and multiply it by I. Now, what can we do about the inverse factorials? Because as I've mentioned, to calculate, and well, by definition, to calculate the binomial coefficient n choose k, we have to take n factorial and divide it by k factorial and then minus k factorial. I've earlier told you that modulo p, and will always work modulo p, a to the power of p minus 2 is equal to a to the minus 1. That is the inverse of a, which really is what we refer here by dividing by k factorial. But we do not need to calculate the inverse of k factorial or of any factorial every time we try to find a binomial coefficient. Firstly, technically, we can do that at the very beginning. We can just make initialize a new array and calculate the inverses of factorials as exponentiating the same factorials to the power of p minus 2. But this has complexity of n log, and it might harm us in the process in some cases, which is unpreferable, because we can do better in O(n) using a little smart trick. Specifically, if we are to calculate the inverse factorial of n factorial, so inverse factorial of n equals n factorial to the minus 1, we can clearly state in such a case, if we will learn the FFT, well, not today, that's clear. If people vote for it, I will maybe teach it, but I would not really recommend it because it's completely out of the scope of the Olympiad of Informatics. Most importantly, the only thing that would ever make sense to learn, and I say this only because there's been precedent in 2022, I think, is generating functions, but to a very basic level, as what they are, what derivatives of polynomials look like, and basic facts such as the fundamental theorem of algebra or stuff like that. Most notably this because for some contestants, it has been reported to have been very helpful in solving problem circuits of IOI 2022. But other than that, there are no uses for FFT at the Olympiad level, only in ICPC where it can be black boxed. So one can go about all their life and not know how to implement FFT, only know that it multiplies to polynomials. Unless, if you really want to learn FFT, we can make a poll on the Discord, and if it yields out positive, add it to the list of topics. Okay. We can calculate all the inverse factorials by starting with the biggest one of all, n factorial. N factorial to the power of minus 1. Really, we can distribute this minus 1 exponent to every element in this product to get 1 to the minus 1 times 2 to the minus 1 times 3 to the minus 1 times 4 to the minus 1 times literally every single number up to n to the minus 1. This is 2. Why this is useful is because this number is really, wait, sorry. If we look just a bit closer, it's really almost identical as the factorials were before to the inverse factorial of n minus 1. But most notably, it multiplies by n to the power of minus 1 additionally. So it is inverse factorial of n minus 1 times n to the power of minus 1. So I'll rewrite this identity here. Multiplying by n on both sides, we get this. So really, now we can calculate all the inverse factorials upon getting the inverse factorial of the greatest number that, okay, I said small, lowercase n, uppercase n, it's the same. By getting the inverse factorial of the greatest factorial that we want to consider, and then iterating from n up to 0 to get the lesser inverse factorial by means of this formula. Is everything clear so far? Okay, I think it is. So, we are basically done. Now, we can both calculate n choose k, by the k binomial coefficient of n, and a to the power of k. I will now list three identities that I think are useful. There might be obviously more combinatorial identities, but these are the only three that have come to mind when I thought about what would be useful to mention. And most notably and famously, the stars and bars identity, which says that at its most trivial form, that for it seeks to calculate the number of, oh my god, no, the number of tuples x1, x2, xk, such that k is, okay, actually k doesn't matter, xi is at least 1, and the sum of xi is a given n. So this would be stars and bars of n and k. We can calculate this number by trying to make a bijection between all these tuples that we seek to count and binary strings. Or the initial variant is to do with stars and bars, but when I was but a little child, every time I thought about choosing the stars out of the bars, I've been confused, and then someone told me binary strings, and I thought that actually makes sense. So I'll just present it as binary strings, but they're actually equivalent. I mean, they really say the same thing, only one uses stars and the other uses zeros. So out of nowhere, and I apologize for that, let's consider all the binary strings uh, of length n with k bits. Sorry, k minus 1 bits turned on. So for let's say n equals 5 and k equals 3, let's consider all the, how many are they? All the 10 binary strings. Oh God. I'll write them up here. So it's 1 1 0 0 0 1 0 1 0 0 1 0 0 1 0. Okay, I won't actually get to do it because I'm bored. Okay, I'll draw a few more. 0 0 1 0 1 and 0 1 0 0 1. But that's it. I'm done. That more than half. What these binary strings can help us is in the following way. We established that, wait, no, of length n minus 1, sorry. We established the following way to transform a binary string back to such a tuple of k non-negative of k positive integers such that their sum is equal to n. So wait, for this case then it's n equals 6 and k equals 3. X1 will be the number of zeros up to the first bit. Plus 1. X2 will be equal to the number of zeros up to a second bit, plus 1 again, and so on. So basically, what this will give us is x1 will be equal to 2, these two, and these two entries, and x2 will be equal again to 2, these next two entries. Now, well, clearly, I've only mentioned two numbers when initially I've said these strings will generate 3. The third one will be then the number of zeros at the end plus 1. Basically, what happens is that we just assume that there is a ghost bit of 1 over here, and that each one delimitates a segment for its own. So this one over here would delimitate this segment. The next one would delimitate everything from the last one to itself, so this bucket, and then the last one will delimitate everything from the previous one, the second one, and up to it. In this case, we get this segment, and this segment. And obviously, the length of the segments is having n-1 bits in the bit string plus the one artificially added one equal to 6. But how do we choose? We choose k bits from n. This is by definition n choose k. This, I hope everyone agrees with that. So in this case, back to the original problem. The number of ways to choose k numbers such that all of these numbers are at least 1 and their sum is equal to n, noted as SB of n and k, well, not really, no one denotes it like that, but whatever, is equal to n minus 1 choose k minus 1. Yes, so the problem that Shohrukh sent is related to this. Only that the problem on success describes a different variant of the same problem that really does not, as I think it's the saying in English, maybe it's, of course, that in English, I'm not sure, the apple does not fall far from the tree because it's about apples, whatever. Another variant of the same problem would be when we impose that xi is just non-negative and that the sum of xi is still n, still fixed to be equal to n. In such a case, we go back to the binary strings that we mentioned earlier. In this case, before we artificially added 1 because we said that every turned on bit delimitates a segment for itself. This notion of delimiting segments will still persist right now. We will not change it, other than the fact that we will not consider ones to count to the length of the segments. So then, such a partition of bits, well, this is the artificial one over here. So this has 5 bits to turned on. Such a binary string would imply the solution x1 equals 1, x2 equals 2, and x3 equals 0. So the count of zeros up to the 1. So then, in this case, because the sum of xi's is equal to n, but we now know that xi's correlate with the zeros in the bit string, we'll have to make special room for the ones that we no longer calculate. So we know that we have one at the end of the bit string that we forcibly add. So we have that one. So out of k turned on bits, one is forced. And the other k minus 1 have to also belong to the bit string. So we have k minus 1 bits of 1 that have to appear somewhere in the bit string. And we know that there are n bits that are turned off to 0. And out of these n plus k minus 1, we have to choose k minus 1. I think normally when someone talks about stars and bars, this is actually the identity that they are talking about. This n plus k minus 1, choose k minus 1. This solves the problem when xi is at least 0. I will also mention very briefly that when uh, xi is forced to be equal than a, but for all I, so for a constant a, this uh, formula, as we might interpolate by now, shifts to n plus k minus 1 minus, I think it's minus, is it minus? Yeah, it is. Minus a times k minus 1, choose k minus 1. For similar reasons as before, because, for example, if a were to be equal to 3, then when we said xi is greater than 1, we counted the 1. But now, in the final bit string, we know that we have to add for each xi another, not only the ones, but also another 2 zeros in the bit string that are forced. So every time we would see a 1, we would have to add 2 zeros behind it. So then the question becomes, in how many ways can we permute constructs of the form 001 with constructs of the form 0, where the zeros are just adding extra ones on top of the minimal solution where xi equals a. And this similarly works if a is negative, but I'm not sure any of these cases will ever be will ever appear in a problem. But I think it's good to know. Finally, there's one more variant that I need to mention. When instead of having the sum of xi's equals n, it would be equal to less than n, less or equal to n. In such a case, we can consider that we would really want to count not tuples of k elements all greater than 1 or whatever value we choose here, a, but let's stick with 1, such that their sum is less than or equal to n, but the count of tuples of length k plus 1 which, and I'll note the last value as a slack variable because I think that's what it's called in other places, most notably in simplex. We'll add a slack variable such that this value will be equal to n minus the sum of the xi's. So to say that by the end we will have a tuple where the sum of xi's plus this newly added value will be equal to n, which is really the initial problem. So if we meet such a problem where sum of xi is less than or equal to n, we can add the slack variable and be done with it. Unfortunately, without me realizing this, I've created a particular case that is quite funny because in this scenario that I've proposed to you, all these values have to be greater or equal to 1, but s is not really forced. It can be equal to 0. In this case, we can, just as before, when we try to put xi greater than a, and we've said that we'll fix for each one to have some zeros before it, just like that, or that each one would weigh more zeros. So we'd have to eliminate some of the zeros that we'd add in the bit string that we'd normally consider. In this case, we can consider that whereas normally I've said in this case, the last one would still delimitate a segment and result in a positive length for its own, that it just doesn't. which doesn't really change the fact by much, to say that now we have to choose out of n total bits, because basically what we can do is just say that we want the sum to be equal to n plus 1, and just like that, s becomes greater than or equal to 1, but whatever. So n total bits with k bits turned on. This yields and choose k, just like that. So to recap, the number of tuples such that the sum of the elements in the tuples in the tuple is less than or equal to n, so less than or equal to n, and each element is at least 1, is equal to n choose k. Similarly, if these values can be non-negative, then the result then would be n plus k choose k. All that happened was that we artificially introduced another variable to go back to the original problem where the sum of the elements in the tuple was equal to n, or at least to some constant that we knew about. Are there any questions? If not, I will move on to the second identity, and then the third. Without changing much from these bit strings that I've talked about, let's now consider the following and maybe irritating sum. What was it? Okay, sum of k I squared. Does someone know how to solve this identity? If they do, good job, I think. Maybe you're free to raise your hand if you want to, but whatever. This is, I think, a special case of what I hope is called the Vandermonde identity. Which states that for any A and B, what was it? I think it was trivially something like sum of A and B, sorry, A, B, and K. For every I from 0 up to K, we consider A choose I times B choose K minus I. Let me actually check if that's it. That is it. The Vandermonde identity states that okay, that looks awfully lot like a plus. That this identity is equal to A plus B choose K. We can again think about binary strings, in that this will be just a binary string with length A plus B, and number of turned on bits equal to k. Whereas let's consider what value we are calculating for some I, for some arbitrary I. For any I, we are basically calculating the number of bit strings, I'll say BS because I'm bored, with length A and number of ones equal I. And here we have length B and number of ones equal to K minus I. But if we are to concatenate all the bit strings that we would ever obtain, we would get, I'll move here. So we would get a binary string of length A with I bits and of length A and I bits, and the binary string of length B with K minus I bits. But together they form one binary string of length A plus B and K bits, because we have I bits in the I turned on bits in the left half and K minus I in the right half. The reason for which this sum is not less than or equal to this, or actually calculates it well and does not double count. Wait. Sorry. If it's been cleared up. There's an unfortunate delay between the times that I see the messages and when I get to respond to them. Okay, if there's there are no more inclarities, I will continue. The reason for which this sum perfectly describes this and doesn't only calculate some bit strings but doesn't double count them. Obviously, double counting is not an issue for any term of the sequence, but it might be the case that any later sum would double count the same binary string that we calculated, and so on, is that for any binary string of length A plus B, clearly we can split it into two halves of length A and of length B, so B and A, and clearly this half will have some number of ones, and this will have K minus that number of ones from before. So just for all of these reasons, we know that this bit string will be calculated at some point in the sum uniquely. And now, to go back to the question I initially posed to you, we can shift this sum. Okay, it's from I0 to I plus K. We can change the sum that we calculate to K choose I times K choose K minus I, because it is well known that the n choose K equals n choose n minus K. This would be because if we are in a bit string to calculate the number of strings, bit strings of length n with K bits, K turned on bits, it would be equivalent to calculating the number of bit strings of length n with n minus K of bits. So we can change one of the terms from this summation to K minus I, and now we have this iterated I from 0 to K, where the second coefficient of the uh, binomial coefficient, the second parameter of the binomial coefficient in one of them goes up, and in the other it goes down, which is, well, really what we had in the van der Waals identity before us. Sum of I from 0 to k of a choose I times b choose k minus I equals a plus b choose k. So this would be equal to k choose k. There will be a problem included where this identity is useful. I mean, only mention I only mention it because it is useful, obviously, and you might encounter it. Now I'm solving of some x up to n. There is no n. There is k and n. All the summations I've done are basically for normally when someone just writes sum of xi, they really mean I from negative infinity. They might as well mean I from negative infinity to infinity. And a special case that I've basically overlooked here for the sake of brevity, but now I will because why not? Is when, for example, a would be equal to 3, b would be equal to 11, and k would be equal to 5. Then I've said that we divide a bit string of length 14 into a half of length 3 and a half of length 11. And we count the number of ones in the half of length 3, and then that is at what time the bit string is calculated in the original summation. But a half of length 3 cannot have 5 bits. So why does I go from 0 to 5 and not to 3 or whatever? It is generally considered that n choose k for k greater than n or k less than 0 is equal to 0. So for this reason, in such a sum, it will be annulled. It won't appear. And similarly, in many cases when a summation is mentioned but without any indices from where it would end and where it would start, many of the elements will be 0 except for the ones that we technically care more about. So I hope that answers the question. Wait, which I've answered like again 3 minutes later than when it was asked. I'll wait a minute. If there are any questions regarding this. Okay, one question. Let's go. Okay, table up until we get the question. Uh, no, it's exponented to the power of 2. Uh, the issue with, okay, maybe I should address this. The issue with this identity going to another exponent, let's say 3, is that uh, it is not well described in such a case because we had one single iteration over this index in the original sum because we split the bit string of which we already knew the count of ones was equal to k into a smaller piece for which we didn't know about, but for which the latter piece was deducible from this constant and whatever we fixed here. But if you were to have, let's say in this case, sum of k choose I to the power of 3, then it would mean that the final bit string would have, if we are to make the same reasoning, we would split it into thirds. For the whole array, we know that the count of ones will be equal to something. Let's assume we do. But then we have to fix both the count of ones in the first half, the count of ones in the second half, to get the count of ones in the third half. The reason for which this worked here was because, as I said earlier, we changed this to product of k times choose I times k choose k minus I, which better reflected the original Vandermonde identity. But in such a case, it wouldn't really make much sense. It won't lead to anything, except if we sum over I, then sum over j of k choose I, and maybe then, no, actually no, k choose I, k choose j, and then k choose some c minus I minus j. And only this sum would ever make sense to be equal to 3k choose c, whatever that c is. Is that clear? Okay. And finally, I think maybe the most famous one of all, at least the one I feel is a bit more notorious, is the hockey stick identity. And Pascal's triangle, for that matter. Okay, so I think this is called Pascal's identity. The following, which does not really deserve a lot of time spent on it. It says as follows. N choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. This comes from the following simple fact. If we want to choose k out of n bits which k to be turned on, we can, as almost similarly to what we've mentioned before, we either create a bit string of length n minus 1 with k turned on bits, and then the last bit will be turned on 0, or we create a bit string of length minus 1 with k minus 1 turned on bits, forcing the last bit to be equal to 1. So if you will, actually this is a trivial case of van der Waals identity where A equals 1, B equals n minus 1, and K equals, well, K. Yeah, because 1 choose 1 and 1 choose 0 are both 1. Why this is important is because sometimes, but not always, but sometimes it is useful to plot these binomial coefficients into a 2D plane. That is, because there are two parameters, what if we would observe them as points or in a grid? But most famously, this is represented about the problem or with the hockey stick. Okay, I'll share it, but it's in Romanian, and I'll make a VJudge with all the problems that are to be that are left as homework if I don't get to talk about any of them in a VJudge. So that problem will also appear there. Let me one moment. I think you can translate with again with VJudge until I get to compile the set. Actually, I can just mention it here. So the problem with okay, before introducing that problem, wait. Oh God. Okay, it's reducible. So I first have to introduce Pascal's triangle. What it does is, as I said, plot all the binomial coefficients in the plane, but as a triangle. So on row number 0, we'll have 0 choose 0. On row number 1, we'll have 1 choose 0 and 1 choose 1. On row number 2, we'll have 2 choose 0, 2 choose 1, and 2 choose 2. On row number 3, we have 1, 3, 3, 1. On row number 4, we have 1, 4, 6, 4, 1. 5 is 1, 5, 10, 10, 5, 1. The reason why this structure emerged is to make use of this identity. Most notably because we can observe that for any number, if, as I've drawn them, we look at the element on the line before and to the left, and to the line before and to the right, this element constitutes the sum of those two numbers. 6 is the sum of 3 and 3. 10 is the sum of 6 and 4. Most notably because of this. Although it would have been interesting not to jump so fast into this, but unfortunately, this is what had to happen because I don't think we have much time, and I wanted to cover the principle of inclusion and exclusion as well. A problem that was set in some contest, Junior TST of Romania, a lot of years ago, said something like this. So consider the Pascal's triangle. I'll redraw it to be more coherent. 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and so on. I won't draw another line because I'm bored. Okay, consider a subtriangle of Pascal's triangle. The dimensions of this triangle will be like around 10 to the power of 6. Obviously, unfortunately, the triangle will be equilateral because we can't really choose a different triangle than that. And given the coordinates of this triangle, so then the top corner of the triangle and the length of the triangle that we seek to calculate, what is the sum of all the binomial coefficients in Pascal's triangle with this with these coordinates. So then I think formally this reduces to, so for an A and B with A greater than B and K, for I from 0 to that K, well, maybe K minus 1, but whatever, doesn't matter. Sum from I from 0 to K to sum of J from 0 to I with A plus I choose B plus J, with all of these numbers equal to like 10 to the power of 6 or whatever. Is the task clear before we move on? Good. The hockey stick identity tries to do the following thing. Unfortunately, I'll have to redraw Pascal's triangle to my demise and offset 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. It basically says the following thing, I think. For an A, B, and a K, which is a bit similar to what we had before, but who was to say that this is how to solve the problem? For I from 0 to that very same K, sum over A plus I choose B plus I equals, I think it's A plus K choose B plus K plus 1 minus, so A choose B plus 1. This emerges from the following simple fact. Let's say that we add this term to this sum over here. This sum, represented on the Pascal's triangle, initially would look something like this. So it's 3 plus 6 plus 10 plus 15. So it's basically a line parallel to the one of the initial sides of the triangle. It might as well be in the other direction, but we ignore that orientation because it's irrelevant. For such a case, we consider, as I've said, adding this element to the sum, which in this case would be this element. But using Pascal's identity, we can simplify the sum of 3 plus 1 to get 4. The 4 that is actually a binomial coefficient on its own. Wait, what did I do? So we can ignore these two, and now we have, instead of 3 plus 1 plus 6 plus 10 plus 15, we have 6 plus 4 plus 10 plus 15. Again, 6 plus 4 yields another binomial coefficient on the following line. So we can reduce this and go on the next line. 10 plus 10 yields another binomial coefficient, which is 20, so we can ignore these. And now we've reduced the sum to 15 plus 20. 1, 7, 21, 35, 35, 21, 7, 1. And similarly, now that we have two adjacent elements in the Pascal's triangle, we can again simplify these two to get another binomial coefficient. The reason why this is called the hockey stick identity Wait. No. Oh, God. Okay. Too bad. Okay. More. That's really sad. 4, 3, 1. Sorry. 6, 4, 10, 10, 15, 20, 15, 35, 35, 21, 7, 1. Is because the initial sum that we sought to calculate looked like a tail. And ignoring this element, the final element of the summation will be the very next element, but sort of slanted on the line that we've established. And it looks like a hockey stick because it's very long, and then at the end it just curves perpendicularly, as you can see here. Most naturally, this sum starts with a no a equals b. So basically, on the upper, it starts a bit up higher up, and so then this sum would normally not have a different b or whatever. But then the form I've given you is an extension of this by partial sums, because if we know that this sum, wait, Christ, this sum is equal to some element here, and this sum is equal to some element here, then obviously this sum is equal to the difference between this element and this element. All of this to say that in the Pascal's triangle, each new diagonal is the prefix sum of the earlier one, which in generating functions, I will just mention it because I'm really bored, is also known as 1 to 1 over x to some power of k. But doesn't matter. Maybe we'll get to that if people want to discuss those things. Is everything clear so far? Okay, I think it might be. So I hope everything is here. No, I didn't. Oh no, not the task. Okay, now back to the task that I've mentioned before. Normally, clearly, this initial sum that we had a lot of elements. It had around k squared elements, and we could have summed up each of these binomial coefficients one by one, because obviously it would be time limit given the k is around 1,000,000. But now we can reduce this triangle with the hockey stick identity to the following binomial coefficients. So this sum will be equal to this minus, well, it's fine, red b plus, but whatever. So this minus this, then this binomial coefficient will be this minus this, and then this binomial coefficient, which is one of its own, but whatever, will be this, no, sorry, 15 minus 5. So you basically have now a sum of binomial coefficients on one of the lines of Pascal's triangle minus another binomial coefficient from one column, so to say, or another diagonal from Pascal's triangle. If we are lazy, this scion sum can also be visibly reduced by hockey sticks by the hockey stick identity, but it's not really necessary. Yeah, that would be Do we have, how much time do we have left? How can we calculate the values inside the red and blue circles fast? Well, given that the count of red circles and blue circles is related to the count of diagonals in the original triangle where we wanted to make the summation, which is actually k. We have k red circles and we have k blue circles. Then what remains is to be able to calculate any binomial coefficient of the form n, which is k, where n factorial over k factorial times n minus k factorial fast. And as we've discussed, we can do this by first initializing the all the factorials that we need, in this case up to 10 to the power of 6 or 10 to the power, 2 times 10 to the power of 6 or whatever. Then calculating similarly the, oh my god, the inverse factorials by means of this formula, where we initially calculate the inverse factorial of n factorial. We have now, we now have 1 to the minus 1 times 2 to the minus 2 times 3 to the minus, and so on. And then all other smaller inverse factorials follow from this simple recurrence, where inverse factorial of n times n equals inverse factorial of n minus 1. Is that clear? How can we calculate values from these circles fast? I mentioned that I think up to like a few years ago, but I'm not sure when. Normally, it was expected that the following sum cannot be done better than linearly, or if not linearly, then maybe some conditions on the problem that would have simplified it. So the following sum could have been calculated much more easily. Sum of A choose B plus I, which is basically a sum of elements on the same line. But I think some Chinese kid a few years ago found another algorithm where he interpolates some, I don't know which thing, and for a lot of such queries, you can calculate them in n log squared. Or so there's a blog on Code Forces, and I'll try to find it, but I myself don't understand it, or never took time to understand it, and it's a bit beyond the scope of the Olympiad, fortunately. What kind of problems can we use them? Yes, so I normally have a list of tasks prepared for practice for this, and I will share it with you. And yeah, that's it. Normally, so the reason why I've introduced all of these is because it is really important, because many, so informatics generally, or competitive programming is generally the same. I mean, when you solve a problem, there are distinctive traits about that problem, but there is a line between what we can think and what ideas we can come up with because we are really smart or whatever, and then what we can implement, or what we already know and we don't really want to come up with on the spot. The purpose of this lesson was then to first introduce you to how to calculate, I don't think it's no longer here, but how to calculate trivial structures that might emerge with from combinatorical properties. There are a lot of problems on Code Forces. Like most of the times you see 10 to the power of 9 plus 7. It's either a DP that gets too big, or some task where you have to make some formulas that most often do not rely on binomial coefficients, and sometimes even exponentiations or like 2 to the power of x is the number of subsets of a set of like that, so stuff like that. So yeah, there are a lot of problems. I'll prepare the sum of the subtriangle in Pascal's triangle is equal to binomial. Wait, where? No. If you mean this and just k, I just said that we know for each such circle that it is a binomial coefficient, and the binomial coefficient is of the form n choose k, which is calculated as n factorial times k factorial to the -1 times n minus k factorial to the -1. This nk has nothing to do with anything that we have. Actually, I just erase it. But so yeah, what I try to say is that each of the elements in the elements that we've reduced our sum to are binomial coefficients, and we calculate them as previously described. Well, normally I would also like to quickly mention the principle of inclusion-exclusion, and I'll try to be quick in that. The principle of inclusion-exclusion is just basically every time that it appears, normally it appears under multiple variants that are not really related, but it generally makes use of the following identity. Whereas x plus 1 to the power of n is equal to x to the power of I times n choose I, because basically we have this x, and in how many ways can we choose x from x I times, where we have a binary option at every step, whether we choose an x or whether we choose a 1, which doesn't really do anything. So this is an identity. This is clear. The principle of inclusion-exclusion mostly relies on the notion that 1 minus 1 to the power of n is 0. But most importantly, it's minus 1 to the power of I times n choose I. And generally in problems, this n choose I is implied. That is, you don't really see it, but you can construct a dp, and generally the form of the dp is dp of something and something. This something represents we will do at least be something. Usually it's mistakes or something like that. We'll do at least b mistakes under the previous parameters. I assume I don't really have time to show a problem using that, but I think we can discuss it in other days. And most notably, problem from today, Kai and N uses this principle, along with some fun divisor facts. I think you have to go now, no? Or do I still have time to present? Reiterate in any case the things that we've learned today. So a to the power of p minus 1 equals 1, implying a to the power of p minus 2 is equal to a minus 1 inverse of a, 1 over a mod p. A to the x can be calculated in of log x. Consider a to the power 2 to the power of I. Factorials can be calculated. We know how to calculate n choose k, and we know now that the sum of I from 0 to k of a plus I choose b plus I equals a choose plus k choose no, a plus k plus 1 choose b plus k plus 2 minus a choose b plus 1. What else? Sum of a choose I times b choose k minus I is a plus b choose k. Wait, focus. I forgot. That's embarrassing. Oh no. I think that's it. Yeah, sorry. So these are the identities that we've covered today. I thought there were three, but I forgot which was the third one. There might have not have been a third one. And I'm just hallucinating. Oh no, stars and bars. Yeah, sorry. And stars and bars, which is the count of x1, xn, such that most most frequently xi is greater than 0 with sum of xi equals n is n plus k minus 1 choose k minus 1. And yeah, this the principle of inclusion exclusion, which is minus 1 minus 1 to the power of n is 0 unless n is equal to 0, then it's equal to 1. Okay. Oh, it doesn't have to. We have an additional 30 minutes. Perfect. So I'll go a bit into depth with the principle of inclusion exclusion here. Okay. The task that I will recommend you think about, I think I've given it to you yesterday. I've put a link to it. I'll remind it. Will be this. Did you have time to think about it? Or did anyone solve it? And if they did, congratulations. Please tell me. I'll congratulate you personally if you did. This task unfortunately also appears on research, but I'm not sure where right now. I don't think I find it. Unfortunately, the problem doesn't have an English translation. Wait, what? It should. Wait, log into this problem. Yeah. So. So on VJudge, normally you'd see the problem. It's not in English. It's in this unintelligible language, whatever it is. but they've added this I don't know, feature where you can request machine translation, and then translation. Usually, it used to be that people would do them by themselves, but they appear as tabs under the user's page. So then, after clicking this, which is in English, uh, now you have the task in English. So I'll leave 5 minutes, I think, for people to read it before I get into it. Is that fine? Yeah, it is related because I think it's a very good example of the principle of inclusion exclusion. I can leave it as homework with the other tasks I've prepared, or I can present it now. But I'm not sure which is preferable. I'd technically prefer to present it now because then we could get to do more stuff tomorrow that would be unrelated to today. Yeah, so 5 minutes I leave for everyone to accommodate themselves with the problem before I get into it. Um, so to start with a very basic fundamental is that obviously uh, so let's take two adjacent elements that might contradict uh, our task to find the absolute difference between any two consecutive elements is not divisible by k. So let's consider two elements. Let's consider a string where there are two elements, two adjacent elements whose difference is divisible by k. This clearly means that A mod k equals B mod k by definition of divisibility. So we can just reduce the array we had, V, to V mod that k. And now the problem asks us to find the number of permutations of V such that uh, adjacent elements after permutation are distinct. This is clear, no? If not, raise your hand because I think it makes a sound when someone raises a hand. Yeah, it makes a sound. So I think actually, whenever someone has a question, please press that raise hand thing. So I'll hear it. Okay. What follows? What could follow is us trying to make a DP. So what would we finally need to calculate in the DP? Well, it's very likely that we can handle everything at once. For instance, but we'd have to add values gradually. I suggest that at first we introduce values in the order of the array, because basically now that we have to deal with permutations, all that we really actually want to is to we can might as well consider that V is sorted, meaning that for each value that we have in V, we really care about its frequency because we don't have to care about anything else regarding those values, given that we'll permit them. So we reduce V to this set of frequencies of identical elements. Sorry, 3. What is important is that these elements that are identical, we will not place them next to each other. So we will construct the solutions incrementally, adding classes of equivalent elements one by one. So the first parameter of the DP, in the spirit to have an ordering in which we can construct solutions, should be, let's call it an n, although n is a bit confusing, but n will be the count of distinct values added. Given that we consider that we always have the smallest n, such values. That is, like, dp of 3 will not ever be 1, will not consider solutions where there is only 1, 2, and 4. We'll have 1, 2, and 3 in the array. So basically, we add these classes one by one. We first consider all the solutions where there is only the value 1, then all the solutions where there is 1 and 2, and all the solutions where there is 1 and 2 and 3, and then 1 and 2 and 3 and 4. When we get to 4, when we get to have inserted all the elements we had, we can state that we finished the problem. Now, what follows naturally, because we want to not have intervals where the values are adjacent, is to have some way of quantifying this information. But obviously, because we add these elements one by one, that is, we basically start with 1, 1, 1, and this is not a correct solution. We cannot take our DP through states which all respect the final destination. There might be states where the condition is not happening, where there are adjacent elements that are equal. In the spirit, it's not useful to only say that this does happen, because it will not help us in any way, because 1, 1, 1 is clearly a very different thing from 1, 1, 2, 1, because here we only have one bad interval to solve. If we have a bunch of 3s, we can just insert any of them here and we would be done. Whereas in this case, we would have to insert 2 3s to solve this, which leads us to consider the second parameter of the DP, which turns out to be enough. The count of i's such that solution of I is equal to solution of I plus 1. Clearly, because we know the count of distinct values that we've added, we also know the set of the number of elements that are in any solution that we've considered so far. So not only do we have the intervals where the values are equal, but we also have the intervals where the values are distinct. I'll change the page. So we have dp of n, and I will note it as k, the count of I such that v of I is equal to v of I plus 1 in the solution we've considered. So we calculate all the solutions with the first 10 distinct values, where these solutions have I adjacent intervals where the values are equal. The problem is that this dp already has like n squared an n-squared recurrence, and it's already pretty bad. And the more we will try to make, the more we'll add to the recurrence to make it valid, it will likely grow to n to the third, n to the fourth, and so on. To illustrate this, let's consider how we would go to the p of n plus 1 and something. To consider this new set of elements, we would first have to consider the following. So we have k bad intervals. We can do the following operations. Solve a bad interval. This is because we put one of the new values, let's call them 3s now. We'll put a 3 between one of the already existing bad intervals. So that's fine. Don't do anything. And create a bad interval. It turns out that normally maybe we'd have to fix 2 of these values to properly have a recurrence that we can model. Specifically, to create a bad interval, that would mean to insert 3s adjacent to one another in the array. And how we can consider this most cleanly is to take the set of all the 3s that we have. We say that we want to create, in this case, let's say 4 bad intervals. In such a case, we'd have to select which of these intervals will be bad and which will not be. Let's say in this case that we will select that we'll insert these 3s in this order. And basically what we'll do is insert these 3s as unique elements. And we will force them in the rest of the recurrence to not be placed one next to another. To solve a bad interval, we just choose which of these go in some of the bad intervals. This is another binomial coefficient. And then the not doing anything is which of these elements would go and how do we distribute them to any of the other intervals that we have. This would maybe look like n to the fourth, but because of a complexity quirk where we basically do the following sum of fi of fj from j equals 0 to j less than I on y equals 0 to n times fi. This sum is O of sum of fi squared, where fi is the frequency of element with value I. This happens, trust me. So then the final complexity is n to the third. What will help us, however, to go from this n to the third step to n to the second is to relax our dp, not to calculate the number of intervals where where k denotes that we have a specifically vi bad elements, but that we have at least k bad intervals. Because of this, we are no longer pressured to, after establishing which new bad intervals we create, to distribute these blocks of 3s into distinct subsequences, which allows us to consider that we aren't really solving bad intervals at all, that we are just throwing these blocks of 3s wherever and whenever, and that we hope that by the end they will be solved. Obviously, then dp of n of 0 will be wrong, will be very wrong. Because essentially what dp of n of 0 will be is permutations with repetitions. We'll insert all of these trees into the array one by one without any regard of to whether we will put them adjacent or not. But if we look at any bad solution, we will see that the number of times it is calculated here is around k to 0, where k is the number of faults that happen in that solution. In dp of n, 1 is k1. I don't have time to explain this, but trust me, and so on. In dp of n j, it is k choose j. And then, so if by the end we sum up dp of n 0, we subtract dp of n 1, and we basically calculate the sum of dp of nj times minus 1 to the power of j, we will have the final solution. This will be the final correct result. I can get into the details because I don't have time. I don't have time right now. But this happens because, as I said, any solution with a positive amount of faults will be annulled here. It will be cancelled. But any solution with exactly 0 faults will be counted exactly one time in dp of n0. And that is it. Okay, I think we can end now because I think I have to end now. I will shortly provide VJudge with the practice problems, and I guess we'll see each other tomorrow. Goodbye.